The AH-1G helicopter includes the most advanced armament systems, ranging from large caliber guns to rockets. Yet no matter how accurate these weapons might be, their systems accuracy is dependent upon aircraft stability. The error cone for a weapon is influenced by aircraft movements around three axes: pitch, roll, and yaw. Errors in fire direction can be induced through weapon recoil moving the airframe, aerodynamic gusts pushing the aircraft or rotor system, and other mechanisms being established from the flight environment. Therefore, accurate fire coverage is dependent upon the basic stability of the airframe under all flight conditions, hover and forward modes, leading to the axiom of design that stability yields accuracy. During the design of the AH-1G, this axiom was applied. The experience gained with the UH-1C and UH-1D pointed to the two major design requirements. First, the stability system must provide immediate damping of the airframe from external disturbances, and this must be done so that wide-angle weapons coverage and rapid-fire capability were not impaired. Second, the system must work with the pilot at all times to assure him of positive, high-quality flight control response. Two means of providing stability to helicopters are available: mechanical systems and electromechanical systems. On the UH-1 helicopters, stability is achieved by the use of a stabilizer bar assembly attached to the main rotor. As the rotor system turns, the stabilizer bar turns with it. And since the bar is a carefully balanced dynamic system, it develops inertia and gyroscopic forces. These stabilizing forces are induced into the main rotor. The pilot's control forces are also fed through the stabilizer bar into the rotor blades. Because both types of inputs, pilot and inertial, are feeding together, a compromise between pilot control and stabilization occurs. This technique is adequate for a troop transport, but is entirely inadequate for use on the AH-1G. Control response for airframe damping and pilot handling cannot be solved utilizing a mechanical system. Electromechanical systems, as opposed to mechanical stability systems, use an electrical network in conjunction with mechanical devices. A sensing device, such as a rate gyro, is used to provide electrical signals into the network. The network then converts them into commands for the mechanical input into the flight control system. This is done in addition to and concurrent with the inputs made by the pilot. There are two categories of electromechanical stability systems: single loop, usually called ASE or automatic stabilization equipment, and multi-loop type, often called SAS, for stability augmentation system. Neither one of these is an autopilot system. An autopilot has a completely different function. Dismiss this term entirely. A multi-loop stability augmentation system is used on the AH-1G. It provides for airframe damping and also allows the pilot to override the system commands if he desires. Airframe damping occurs in a similar manner to a single-loop system, but the override feature utilizes an extra electrical signal network. The SAS system is integrated with the conventional helicopter flight controls to provide three-axis stabilization and control of the aircraft. Three basic loops are used in the system: the rate gyros, the control motion transducers, and the actuator feedback transducers. In order to better understand the components of the SAS, it is important to understand what a transducer is. The role of a transducer is to convert one form of energy into another. For instance, a photocell is a transducer. It converts the electromagnetic energy incident upon its sensitive face in the form of light waves into an electrical current. Likewise, a potentiometer is a transducer. It can convert mechanical energy, measured in the form of a change in length, such as the movement of a piston, into electrical energy, or as a change in voltage through its circuitry. Transducers allow mechanical motion to be interpreted electrically. The SAS is a three-axis stability augmentation system. Therefore, it is integrated into the cyclic and directional aircraft flight control systems. The first is the fore and aft cyclic control for aircraft pitch changes. The second is the lateral cyclic control for control in roll. And third, the directional control system for changes about the yaw axis. Pilot inputs through the cyclic stick and rudder pedals, whether in pitch, roll, or yaw, all feed through the SAS system. It is important to realize that when the SAS is turned off, the flight controls operate in the conventional manner. With the SAS in operation, an additional mechanical input to the pitch, roll, and yaw flight controls is added to each. Let's move on to the SAS trainer, where the functioning of the individual components can be better understood, since there are no other elements to distract us. Three electrical signals are used in the SAS system. The first comes from the control motion transducers, located in three separate spots within the aircraft push-pull mechanical flight control system. These transducers are linear potentiometers which convert movement of the control rods through a bell crank into a forward feed loop input signal to the compensating circuit. This signal feeds into the sensor amplifier unit, where it is summoned, shaped, and mixed electronically with the rate gyro signal. Mixing occurs in the compensating network. The second signal from the rate gyro occurs when the aircraft pitches, rolls, or yaws, whether pilot-induced or caused by other forces acting on the airframe. If the pilot is not inducing changes and aircraft movement occurs, the rate gyro sends a signal to the compensating network. It is then passed onto the valve driver amplifier module, causing the actuator servo to extend or retract the actuator to correct for the deviation. The third signal comes from the actuator feedback transducer. This component is a linear variable differential transformer mounted internally in the actuator. It provides position information on the actuator when the actuator extends or retracts to return the actuator to the neutral position. All three of these signals, rate gyro, control motion transducer output, and feedback transducer output, are fed into the sensor amplifier compensating network, where they are processed and provided as a correction signal to the valve driver amplifier and the servo valve. The compensating network is actually a printed circuit board with all of its integrated components in a central location. The valve driver amplifier is an encapsulated module located on each circuit board. This component provides the signal to the servo valve on each actuator. The servo valve is an integral part of the actuator. Through it, the electrical signal from the SAS loop can become a mechanical force to operate the flight control linkage. The electrical signal from the valve driver amplifier commands the servo valve to post hydraulic fluid so that the actuator linkage is extended or retracted, thereby inducing a change in the aerodynamic surfaces of the helicopter. Electro-hydraulic actuators are installed in each one of the control systems for pitch, roll, and yaw. They have control tubes and clevis attachments for installation in the control system. These actuators are interchangeable. The actuator authority is limited to control movement of 12.5% either side of normal position. And should the hydraulic or electrical system fail, the actuator is designed to automatically center and lock, thereby becoming a rigid mechanical link in the system. This allows the pilot to fly using normal mechanical control. Circuit protection for the SAS is handled through a 5-amp DC breaker located on the aircraft 28-volt DC circuit breaker panel. A 1 amp fuse for 28 volts is located in the sensor amplifier unit, as well as a spare fuse and holder. The third protective unit is a 1 amp AC breaker located on the 115 volt AC circuit breaker panel. The control panel is located only in the pilot's cockpit. This panel controls all the functions of SAS except for emergency disconnect. It contains a 2-position switch which turns power off and on to the DC and AC circuits, and 3 channel engage switches: pitch, roll, and yaw. Closure of each of these switches provides 28 volts DC power to the hydraulic solenoid valves. 3 no-go indicator lights, 1 for each axis, indicate an out-of-tolerance condition or an unexpired warm-up time in the SAS system. The stability augmentation system is dependent on the use of hydraulic components to convert the electrical sensing commands into control link forces. Therefore, it is a vital subsystem. The main hydraulic system for the aircraft is used as a supply for the SAS. The filters used are 10-micron particle pressure inline type. They are replaceable as complete assemblies and are interchangeable in location. When installing each filter, ensure that the arrow labeled on the side of the filter points toward the solenoid valve. Hydraulic pressure is taken from 2 systems for use by the SAS. System number 1 is used to power the actuator for directional control, and system number 2 is used to power the fore and aft and lateral cyclic actuators. The neutral condition in the actuator occurs when the engine is operating. The electrical power is on, and the SAS axis engage switches are on. Hydraulic pressure is supplied to the actuator. In the neutral position, the servo valve does not supply fluid to the piston. Fluid is allowed to flow through an orifice to act upon the spring-loaded locks. Compression of the locks occurs fully at 300 psi. The piston is now free to be moved in either direction. Note that no fluid is acting on the piston at this time. Therefore, the term neutral applies. The actuator retracts when the servo valve moves to allow the fluid to flow into the right-hand piston area and force the piston to the left. Fluid contained in the left piston area flows out the return line. For actuator extension, the reverse process occurs. The servo valve ports the fluid to the left piston area, applying force to the piston face, causing it to move to the right. Note that in both cases of movement, fluid was provided to the lock chambers to keep them released, not interfering with piston travel. SAS is so sensitive that it is impossible for a man to hold the sensor unit steadily enough, even with his hand supported, that signals are not fed into the rotor system. Even the slight pulsations which aren't visible to the eye generate signals through SAS which would provide aircraft damping. To engage the SAS, start the engine using normal operating procedure. After the engine is stabilized, turn the electrical control switch located on the control panel to power. The 3 no-go lights will illuminate and remain on for 15 to 60 seconds, at which time they will go out. The system may now be engaged by switching the axis switches to pitch, roll, and yaw. The system is now functional. In order to disengage the SAS, all 3 axis switches should be moved to off, or the emergency disengage button on the pilot or gunner cyclic grip may be pressed momentarily. Neither one of these steps turns off the electrical power, but simply disconnects the hydraulic power, causing the actuators to become mechanically locked. The entire SAS system, electrical and hydraulic, can be disengaged by turning the power control switch to off. If during the engaging procedure, one or more of the no-go lights fails to go off in the normal time, The built-in test equipment can be used to help find the trouble. The following procedure should be followed. Press the switch on the amplifier unit marked gyro test. Should the light go out, the gyro is faulty. If the light remains on, press the actuator test switch. If the light goes out, the actuator feedback circuitry is faulty. Should neither of these tests locate the trouble, the next step should be to replace the affected channel module. If this fails, a complete ground troubleshooting procedure should be begun. Stability, the dynamic requirement for an effective helicopter weapon system. The stability augmentation system ensures that the AH-1G is a stable weapons delivery platform. It provides rapid control response to wind and gusts and pilot compatibility, the desired features for the Army's newest combat aircraft.